the ocean's loudest animal just went quiet. A sperm whale, 60 tons. As long as a school bus times 3, fires click so powerful they can be felt in your chest from 100 feet away. 230 decibels, louder than a jet engine, louder than a rocket launch, the loudest sound any living thing on Earth has ever made. Then the orcas show up, and everything stops. No clicks, no calls, just silence. For years, scientists had no idea why. Then they started listening more carefully, and what they found rewrote everything we thought we knew about who controls the ocean. We're going to find out why orcas go silent, how sperm whales turned their skull into a sonic weapon, what happened during a 4-hour battle off California, and the secret second language hiding inside whale clicks that no one heard for millions of years. If this is the kind of thing that keeps you up at night, hit like and subscribe. We make this every week. Now, let's dive. A hydrophone sits 300 feet below the surface of the Pacific Ocean. It records everything. Day and night, it picks up the clicks, calls and whistles of every creature passing by. Researchers on the surface watch the data stream in, hour after hour. Then something strange appears on the screen. The orcas go quiet. 1 second, a full pod of killer whales is chatting, clicking, calling to each other across the water. The next second, nothing. Total silence, like someone hit mute on the entire ocean. The researchers check the equipment. Everything is working fine. They look at the sonar, and there it is. A sperm whale is moving into the area. That's all it takes. Scientists have now recorded this pattern dozens of times in different oceans. Orcas and sperm whales are both apex predators. They both sit at the very top of the food chain. Neither one is supposed to fear anything alive in the sea. And yet, the moment these two animals share the same patch of water, something shifts. The orcas stop talking. Here's why that matters. Orcas are one of the most vocal animals on the planet. They use sound to hunt, to navigate, to keep their family together. Sound is how they survive. Going silent is one of the biggest sacrifices an orca can make. They don't do it for nothing. So, the question is, what does a sperm whale have that makes one of Earth's most powerful predators switch off? The answer starts with a number, 230 decibels. To picture that, think about the loudest thing you've ever heard. A firework going off close by, about 140 decibels. A jet engine at takeoff, around 150. Scientists say 150 decibels is enough to permanently damage your hearing in seconds. Now double the energy, double it again, keep going. You still haven't reached the sperm whale. The sperm whale produces the loudest sound ever recorded from any living creature on Earth. Its click is so powerful that researchers who have dived near a clicking sperm whale describe feeling the sound hit them in the chest like a physical punch, not hearing it, feeling it. One diver said it was like being tapped hard by an invisible hand. Another said the pressure wave rattled his vision. And the orca knows this. Orcas have some of the most sensitive hearing in the ocean. They can detect sounds across a huge range of pitches. Sperm whale clicks arrive right in the heart of that range. When a sperm whale fires up its sonar nearby, an orca doesn't just hear it. The orca gets flooded with it. Every click lands like a shout in a silent room. Multiply that by the hundreds of clicks a sperm whale fires per minute, and you start to understand why the orcas go quiet. Silence becomes armor. If the orcas stop making noise, the sperm whale has less information, less data bouncing back, less chance to locate the pod before they're ready to act. But that's only part of the story. The deeper you go into why orcas fall silent, the stranger it gets, because the silence isn't just about fear, it's a weapon. And using it correctly took millions of years of practice. The first thing you need to understand is what the orcas are actually hunting when they choose to go after a sperm whale at all. Most people picture an orca hunt as something loud. The pod calls out, coordinates, crashes through the waves together. And for some orcas, that picture is exactly right. Fish-eating orcas are chatty. They click constantly, whistle to each other, and use a whole library of calls to organize a chase. They can afford to be loud because salmon don't hear in the same range orcas use. The noise doesn't blow the hunt. Mammal hunting orcas work completely differently. When a pod of mammal hunting orcas moves out to find seals, dolphins, or whales, they go dark. No calls, no social whistles, barely any echolocation clicks. Researchers from the University of Alaska attached sensors to 13 of these orcas during summer hunts and tracked every sound they made, or, more precisely, every sound they didn't make. During the 2 hours of near darkness in the far northern summer nights, the orcas were silent and actively hunting. They weren't using vision either. Too dark. So how were they finding prey? They were listening. Seals breathe. Dolphins click. Porpoises squeak. Every animal in the ocean makes noise just by being alive, and the orca figured out that you don't need to broadcast your own signal if your prey is already broadcasting theirs. The mammal hunting orca evolved into a passive system, a receiver. It moves through the dark ocean with its mouth shut, ears wide open, tracking the sounds of everything else. This changes how we think about orca intelligence. Most people admire orcas for what they do. Scientists are now increasingly amazed by what orcas choose not to do. Restraint is a skill. Going quiet when every instinct pushes you to call out to your pod takes coordination. It takes memory. The orcas somehow communicate a silence protocol. They all stop together. They stay stopped. And they move together through the dark without a single sound passing between them. That level of discipline in a social animal is almost unheard of. Here's where sperm whales enter this picture in a new way. When orcas choose to target a sperm whale, they face a very different challenge than hunting a seal. A seal weighs a few hundred pounds. A sperm whale weighs as much as a city bus loaded with passengers. The size difference alone means orcas need a long, coordinated attack. They can't rush in loud and chaotic. They need time, they need patience, and above all, they need the sperm whale not to know exactly where they are before the attack begins. So the silence when sperm whales arrive isn't panic. It's the same switch that flips before any mammal hunt. The orcas are downshifting into predator mode. They're pulling back their sonar, cutting their chatter, and starting to listen for the one piece of information they need. Where is the sperm whale, and which direction is it moving? The problem is that the sperm whale is also listening, and the sperm whale has been refining its ears for longer than orcas have existed as a species. It can hear an orca call from miles away. It processes that information and shares it through its own clicks with every other sperm whale in the area. The silence from the orca side is smart, but the sperm whale isn't giving anything away either. What makes this standoff so strange is that both animals are operating at the edge of what hearing can do, and the weapon one of them carries inside its own skull is so extreme that scientists are still arguing about how it's physically possible. Stand next to a sperm whale on a beach. You won't be looking at its eye first. You won't notice its teeth. The first thing you see is the head. It's enormous in a way that seems wrong. The sperm whale's head takes up 1/3 of its entire body. On a 60-foot whale, that means 20 feet of skull, oil, and tissue sitting in front of the animal's brain. It looks like a submarine with a rectangular nose bolted on. It looks like a mistake. For a long time, scientists thought it must be. The head seemed too big, too heavy, too strange to serve any obvious purpose. They were wrong. Every inch of that head is dedicated to one thing: making sound. Inside the sperm whale's massive forehead sits an organ called the spermaceti organ. It's a cavity the size of a small car, filled with a waxy, golden oil. For 2 centuries, whalers harvested this oil and used it in lamps, in machines, in cosmetics. They called it liquid gold. They had no idea what it actually did. The spermaceti organ is an acoustic lens. Sound travels through it at nearly twice the speed it moves through regular seawater. That speed difference bends and focuses the sound. the same way a curved mirror focuses light into a laser point. The oil turns a raw click into a directed beam, a shaped, aimed, concentrated pulse of energy. But the organ doesn't work alone. Behind it and in front of it sit a series of air-filled sacs, each one acting like a mirror for sound. A click generated at the front of the whale's head bounces backward into the spermaceti organ, ricochets off the rear sac, travels forward again, and exits through the front of the head as an amplified, focused signal. Every bounce adds intensity. The whale's skull functions like a multi-stage amplifier built directly into the animal's body. And then there's the junk. That's the actual scientific name for it. The junk is a second mass of oil-soaked tissue that sits directly in front of the spermaceti organ. It absorbs the outgoing click and shapes it one last time before the sound leaves the whale's body and enters the water. By the time a click exits the sperm whale's head, it has been bounced, shaped, focused, and amplified by one of the most complex natural structures ever discovered in any animal. The result is a sound so extreme that scientists still argue about whether it could, theoretically, stun or even kill smaller prey at close range. There's something else that makes this head unique. The spermaceti organ may also double as a buoyancy system. The oil changes density when it cools. Researchers think the whale can cool the oil by flooding it with seawater through its nasal passages, making the head denser and helping the animal sink faster into the deep. Then it warms the oil back up on the way to the surface. A built-in diving system, running on the same organ that makes the clicks. One structure, two completely different jobs. Sound weapon and depth controller wrapped in the same mass of golden oil. The orca's silence makes more sense now. Whatever lives inside that enormous head is something the orca has learned over millions of years to take very seriously. But to understand just how seriously, you need to hear the click itself. Numbers on their own mean nothing, so forget 230 decibels for a moment and try this instead. You're underwater, you can't see the whale, you're 100 feet away from it. Then it clicks. You don't hear it the way you hear a sound, you feel it. The pressure wave hits your chest before the noise reaches your ears. Your ribcage vibrates. Your vision blurs for a half second. One marine biologist described it as getting tapped sharply by a giant invisible hand. A diver off the coast of Norway said it felt like his whole body rang like a bell. That is what 230 decibels feels like from a distance of 100 feet. Now get closer. A jet engine at full takeoff sits at around 150 decibels. That's already enough to permanently damage your hearing in under a second. A rock concert runs at about 120. Standing next to a jackhammer gets you to around 100. The decibel scale works on a curve, not a straight line. Every 10 decibels is 10 times more powerful than the number before it. That means the sperm whale's click isn't just 80 decibels louder than a jet engine. It carries more energy than a jet engine by a factor that's almost impossible to describe in everyday terms. Scientists at a Danish research station were studying sperm whales in the cold waters off Norway in the early 2000s. They lowered a hydrophone into the deep. When a sperm whale clicked, the needle on their recording equipment buried itself at the far end of the scale. The reading came back at 236 decibels. That is the highest sound level ever recorded from any animal in any ocean in any study ever conducted. But here's what makes it even more unusual. The click lasts less than 1 millisecond. It's not a roar, not a sustained tone. It's a single snap over in less than the time it takes you to blink. That means all of that energy, all of that pressure is packed into one tiny, razor-sharp pulse. No build-up, no warning. Just a burst of force so concentrated that it can travel through the ocean and be detected by equipment more than 60 miles away. 60 miles? That's roughly the distance from downtown Los Angeles to the far edge of the San Fernando Valley and back again. Now think about what that means for an orca. Orcas have highly sensitive hearing. Their best range sits between 18 and 42 kilohertz. Sperm whale clicks, pulse, right through that range. When a sperm whale fires its sonar nearby, the orca isn't just registering a sound, it's absorbing a physical event, and the sperm whale doesn't fire once. It clicks hundreds of times per minute during a dive, each one arriving like a small shockwave into the orca's highly tuned ears. The orca has no defense against it, except distance and silence. But even 60 miles of ocean isn't always enough to escape what the sperm whale is firing. And that's before we talk about what happens when the click hits something alive at close range. Because some scientists think the sperm whale isn't just using its clicks to find food. Some think it's using them to end the hunt before it begins. A click so powerful it doesn't just locate the squid, it stops it dead. The most powerful sound on Earth starts with something called monkey lips. That is the real scientific name for them, not a nickname, not slang. Monkey lips. They're a pair of dense, rubbery folds of tissue tucked deep inside the sperm whale's right nasal passage, just behind the front of its enormous head. Each one is about the size of a large dinner plate, and they are responsible for everything. To make a click, the whale forces pressurized air through its right nasal passage at high speed. The air hits the monkey lips. They snap shut, just like a pair of lips clapping together. That single clap generates the initial sound pulse. The whole event takes less than 1 millisecond. Then the sound doesn't escape into the water right away. It bounces. The initial click travels backward through the nasal passage and slams into an air-filled sac at the rear of the head called the frontal air sac. That sac acts like a mirror. The sound bounces forward again, now traveling through the spermaceti organ, gathering focus and intensity as the oil bends the wave and concentrates it. It then hits another sac at the front of the head, another bounce, another reflection. By the time the click exits the whale's head and enters the water, it has ricocheted through the skull multiple times, each pass adding direction and power. What the whale produces isn't a single click in the way you might snap your fingers. It's actually a series of pulses in extremely rapid sequence, all generated from that one original lip snap. The interpulse interval, the tiny gap between each copy of the original sound, is so precise that scientists can use it to estimate the physical length of the whale's head. The bigger the head, the longer the round trip for the sound. It's like measuring a room by timing an echo. Here is the part that becomes hard to believe. This system works at depth. At 1,000 feet below the surface, the water pressure squeezes the whale's body from all sides. Air compresses. The nasal passages shrink. Most sound-producing systems in any animal would collapse under those conditions. The sperm whale's system doesn't. Studies where researchers attached acoustic tags to diving whales confirmed that the click output stays almost completely constant down to the deepest dives. The whale can produce the same intensity of sound at the bottom of its dive as it does at the surface. Researchers think the monkey lips mechanism is so simple and so mechanically robust that pressure can't stop it. The lips just need air and force. As long as the whale can push air through the passage, the lips will snap, and the whale's body stores enough air to keep clicking for the entire length of a dive, even as that air shrinks to a small fraction of its surface volume. One more thing, the whale can aim the click. Muscles surrounding the spermaceti organ and the junk allow the whale to subtly change the shape of both structures. This shifts the direction of the outgoing beam. The whale can sweep its sonar across the dark ocean below it, like a spotlight moving across a stage, looking for the shape of a squid hiding in the deep. And every few seconds, with that same tiny snap deep inside its skull, it fires again. The orca, somewhere above, hears every single one and stays completely still. Think about how a satellite dish works. The dish has a curved surface that catches incoming signals from space, bounces them all toward a single point in the center, and feeds a concentrated beam into the receiver. One small receiver, enormous incoming signal. The shape of the dish does all the work. The sperm whale's head is that dish. But instead of catching signals, it's firing them. The spermaceti organ runs almost the full length of the whale's forehead. It's a barrel-shaped cavity sealed inside a case of tough connective tissue, and it's filled entirely with liquid oil. The oil has a very specific property. Sound travels through it at nearly double the speed it moves through seawater. That speed difference is crucial. When a sound wave crosses the boundary between two materials, where it travels at different speeds, it bends. Physicists call this refraction. The sperm whale's head uses refraction the same way a lens uses it to focus light. The original click from the monkey lips enters the rear of the spermaceti organ as a spreading wave. As it moves through the oil, it bends. The shape of the organ curves that spreading wave inward. By the time the click exits the front of the organ, the wave has been pulled back together into a tight directional beam. This is the same principle engineers use in sonar arrays. The sperm whale evolved it independently in biological tissue over tens of millions of years. But the shaping doesn't stop there. Between the spermaceti organ and the outside world sits the junk. Despite its name, the junk is one of the most complex tissues in any living animal. It's a dense layering of oil-filled sacs and connective tissue arranged in a very specific pattern. Each layer has slightly different acoustic properties. As the click passes through the junk on its way out, each layer adds one more small refinement to the beam's shape and direction. The effect is similar to a compound lens in a camera. Multiple elements, each doing a slightly different job, all working together to produce a sharper final image. The result is a click that exits the whale's head as a narrow, focused cone of pressure. Not a sphere spreading in all directions, but a targeted beam aimed at whatever the whale is looking for. Here's where it gets important for orcas. The sperm whale typically aims its sonar downward, toward the deep water where squid live. When a sperm whale is hunting, and an orca approaches from above and behind, the whale's clicks aren't aimed at the orca. But that doesn't make the orca safe. Sound spreads. Even a tightly focused beam scatters some energy to the sides. At 230 decibels of output, the scatter alone is enough to be felt by anything within a wide radius. The orca knows this. It knows the beam is pointing away from it. But it also knows that if the whale turns, even slightly, the full force of that focused cone could sweep across the orca like a spotlight. That's not a comfortable thing to be near, even for an apex predator. What happens inside an orca's ear when a full sperm whale click hits it head-on? Nobody has tested. Nobody has been willing to find out. Something changes in the water the moment that sound machine starts firing. Sound in air fades fast. A shout carries maybe 100 feet on a calm day. A thunderclap, maybe 20 miles at the absolute limit. Air is thin. Energy spreads and gets absorbed quickly. Water is different. Sound moves through water almost 5 times faster than through air. It also holds its energy much longer. The ocean is, acoustically speaking, a nearly perfect medium for long-distance communication. And the deep ocean has something else, a layer called the sound channel. Between roughly 300 and 3,000 feet deep, there's a zone where temperature and pressure create the ideal conditions for sound to travel horizontally with almost no loss. Sound entering the channel gets trapped. It bounces gently between the upper and lower boundaries and can travel for hundreds of miles without fading significantly. Whales have been using this channel for communication for millions of years. A sperm whale click, starting at 230 decibels, entering this channel during a deep dive, can be detected by sensitive equipment more than 60 miles from the source. 60 miles is the distance between Philadelphia and New York City. The click crosses that gap in under a minute. But here is the part that isn't usually discussed. The click doesn't just carry information about where the whale is. It carries information about the whale itself. From a single click, a trained researcher can estimate the length of the animal's head, and from that, its approximate size. Different individual sperm whales have slightly different click patterns, shaped by the unique dimensions of their skulls. Scientists have used this to identify specific individuals without ever seeing them. A whale has an acoustic fingerprint as distinct as a human face, And there is more. Different sperm whale clans, groups that travel together across ocean basins, produce clicks in different rhythmic patterns. These patterns are called codas. One clan in the Pacific uses a pattern that sounds like 5 quick taps followed by a pause. A clan in the Atlantic uses a completely different sequence. Calves learn the coda of their mothers and their group. Codas are cultural. They are passed down through generations the way a dialect passes through a human community. An orca listening to approaching sperm whale clicks isn't just hearing a noise. It's receiving a transmission. It knows how big the whale is. It may know which group it belongs to. It knows how far away it is and in which direction. It knows whether the whale is diving deep or hovering near the surface. All of this comes from a single click, arriving 60 miles before the whale itself does. And sperm whales can hear orca calls from similar distances. The moment an orca pod begins vocalizing anywhere within range, every sperm whale in the area gets the alarm. Some researchers believe sperm whale groups relay this information to each other through their own codas, a warning system that moves through the ocean faster than any ship, covering vast stretches of open water in minutes. By the time orcas are within striking distance, the sperm whales may already know exactly how many there are and what direction they're coming from. The ocean isn't silent, it's full of messages. And both of these animals have spent millions of years learning how to read them. What no one expected is what happens when those messages contain something that sounds like language. A sperm whale dives 3,000 feet into total darkness. No light reaches here. The pressure at this depth would crush a car engine. The whale has been down for 30 minutes and it's still going. It's hunting giant squid. And the squid, some of them 30 feet long and armed with suckers lined with teeth, are fast. They can move. They can fight back. How does an animal with no arms, no hands, and limited speed in open water catch something that agile in pure darkness? The answer scientists have been arguing about for decades. It blasts them with sound. The biological Big Bang hypothesis. That's what researchers call it. The idea is that a sperm whale's click, at close range, can produce a pressure wave intense enough to stun the muscles of a squid, interrupt its nervous system, and freeze it in place for long enough for the whale to close the gap and swallow it, like a stun gun made of sound. The evidence is indirect but compelling. Blind sperm whales have been found in the wild, healthy and well-fed, with full stomachs. These animals couldn't possibly be catching fast-moving squid by sight or by speed alone. Something else is doing the work. The clicks are the only candidate that makes physical sense. Studies of squid nervous systems show that high-pressure pulses can disrupt muscle control, at least at certain intensities. The sperm whale fires not just one click, but rapid sequences called creaks, with the click rate accelerating as the whale closes in on prey, similar to the way a bat speeds up its echolocation right before a catch. Some researchers think the acceleration serves double duty, first to locate the squid precisely, then to saturate it with pressure at close range. One study attached cameras and sensors to sperm whales and captured moments where the whale's body twisted sharply toward prey at depth. The motion was fast, far faster than anyone expected from an animal that size. And in the seconds before the twist, the click rate had jumped dramatically. The squid didn't appear to move away. It just stopped. There's a reason scientists label this a theory. No one has directly observed a squid being stunned by a sperm whale click at depth in real time. Proving it cleanly is extremely difficult. The ocean is dark, the dives are deep, and attaching cameras to animals that can crush your equipment at 3,000 feet is not easy work, but the physics supports it. At the distance a whale would be during a final approach, the click intensity at the squid's location could plausibly exceed the threshold for disrupting soft tissue function in a small animal. Biologists studying the acoustic properties of squid tissue say it's possible. Some say it's probable. If it's true, the sperm whale doesn't just use sound to find prey. It uses sound as a weapon, a biological weapon built into its own skull And now picture what that weapon means in the context of a conflict with an orca. The orca knows what that head can do. It has known, genetically, for millions of years. Every orca alive today descends from ancestors that learned to be careful around these clicks. The ones that weren't careful enough didn't survive to have descendants. This is why the silence falls when sperm whales arrive. What no one expected is that even with that weapon, the sperm whale isn't safe. A fish doesn't know you're coming. Its ears pick up frequencies mostly outside the orca's range. You can shout at the top of your lungs, chase it at full speed, and coordinate loudly with your family the whole time. The salmon has no idea. This is why fish-eating orcas are some of the noisiest animals in the ocean. The noise costs them nothing. A seal is a completely different story. Seals hear well. Dolphins hear even better. Porpoises have evolved to detect the exact frequency range that orcas use to echolocate. Researchers studying this found something remarkable. Some small dolphins and porpoises have shifted their clicks to extremely high frequencies, above what orcas can easily detect. They evolved acoustic camouflage. They made themselves quieter to a predator's ear by moving their signals out of range. This is the acoustic arms race in action. The mammal-hunting orca responded by going dark. If you can't lower your frequency out of the prey's hearing range, you can stop broadcasting altogether. Instead of emitting clicks to find prey, you listen for the sounds the prey is already making. Every seal in the water is breathing, surfacing, possibly calling to others. Every dolphin is chattering in its own dialect. Every porpoise is quietly clicking as it hunts fish. The ocean is never truly silent for an animal with a sharp enough ear. The mammal-hunting orca became a passive receiver, silent, moving, listening. Researcher Volker Dieck and his team in southeastern Alaska attached sensors to 13 of these orcas during active hunts. They recorded every acoustic event and matched it to the orca's movements and hunting success. What they found was clear. During the approach phase, the orcas were almost completely silent. No echolocation, no social calls, no whistles. In one recording from a juvenile orca, the team heard the distant calls of harbor seals getting slowly louder and louder as the orca tracked toward them. Then 3 loud roars from the seals, then sounds of impact, then silence. The orca had tracked those seals entirely by listening to them and had closed the final distance without a single click of its own. After the kill, the orcas became noisy again. They called to each other to coordinate the process of tearing the animal apart, because large prey needs to be shared carefully and efficiently. Communication resumed the moment the silence no longer served a purpose. Sperm whales fall into a strange category in this system. They're not seals. They're not small dolphins. They're the loudest animal on Earth, actively broadcasting their position with 230 decibel pulses every few seconds. There's nothing passive about a sperm whale in the water. It announces itself constantly. So when orcas decide to hunt one, the silence isn't about hiding the approach through acoustic darkness. The sperm whale already knows they're coming. The silence is about something more tactical. By going quiet, the orcas stop feeding the sperm whale new information. Every orca call that travels through the water tells the sperm whale something. How many orcas are present, where they are, how fast they're moving. Cut off the signal, and you cut off the intelligence. The sperm whale knows something is out there. It just can't map it precisely. That small gap in information might be the only edge the orca has. And to use it, the orca pod has to stay coordinated without saying a single word. 40 million years ago, the ancestor of the sperm whale was already in the ocean. It was smaller than today's version, but it had the same basic equipment: a large, oil-filled head and the ability to produce intense directional clicks. The precursors of orcas arrived on the scene much later, around 10 to 11 million years ago. From the moment these two lineages shared the same water, they started changing each other. This is what biologists call coevolution. Two species shaping each other through competition, generation by generation. over millions of years. The sperm whale gets a new adaptation, and the orca adjusts. The orca develops a new strategy, and the sperm whale responds. Back and forth, like two chess players who have been playing the same game for longer than humans have existed. The sperm whale's head grew. That's the most obvious result. The ancestral sperm whale had a much more proportional skull. Over millions of years, natural selection favored individuals with larger heads because larger heads produced more powerful clicks. More powerful clicks meant better hunting at depth, which meant more food, which meant healthier offspring. And at some point, the clicks became powerful enough that they also functioned as a deterrent. A sperm whale with a big enough head could probably push back against smaller predators with sound alone. The orca responded by going quiet. The mammal hunting lineage of orcas progressively reduced its active sound production during hunts. Individuals that stayed noisier lost more prey and faced more counterattacks. Individuals that learned to stay silent had better hunting success. Over generations, silence became the default mode for mammal hunters. The sperm whale then developed more sophisticated hearing to compensate. Its best hearing range sits between 5 and 20 kHz. Orca calls cluster around 1 to 2 kHz, just at the edge of that sensitivity. The sperm whale can still hear them, but it's not the sharpest part of its range. Some researchers think orca calls used to be louder or at a different pitch, and that the sperm whale's hearing gradually shifted to catch what it could. There's a broader consequence here that affects the entire ocean. When orcas avoid an area because of sperm whale presence, every other animal in that area gets a brief reprieve. The pressure that orcas place on seals, dolphins, and fish relaxes temporarily. Food chains shift. Prey populations recover in pockets. The ripple effects of this single predator relationship spread across entire ocean ecosystems. And when sperm whales disappear from an area, maybe due to hunting pressure or climate change, the orcas move in and that buffer disappears. For nearly 2 centuries, humans hunted sperm whales almost to extinction for the oil in their heads. Every sperm whale removed from the ocean wasn't just one less animal. It was one less acoustic presence, one less suppressor of orca activity, one less anchor in a food web that had been balanced around these two predators for millions of years. The oceans are still recovering from that disruption, and the arms race between these two animals is still ongoing. The question is whether the sperm whale's defensive weapons are enough. And to understand the answer, you need to see what happens when orcas stop listening and decide to attack. The orcas have been circling for 20 minutes. They're not rushing. They never rush at this stage. A sperm whale at full size is too dangerous to charge directly. Instead, the orcapod holds a loose perimeter, watching, waiting, reading the movement of the group. The sperm whales know what's coming. Something shifts inside the whale group. They begin to move toward each other, slowly at first. Then, with more urgency, the largest adults push in from the outside. Calves press toward the center. Within minutes, the group has completely changed shape. Where before they were spread over a large patch of ocean, now they form a single tight circle at the surface, every whale pointing outward, their enormous tails fanned around the edge like the petals of a flower. This is the rosette formation. Scientists also call it the marguerite, after the French word for a daisy flower. The name fits. From above, a group of 6 or 8 sperm whales in defensive formation looks exactly like a massive flower floating on the ocean surface. But it's a flower made of weapons. Each adult sperm whale's tail fluke can span over 15 feet across and swing with enough force to kill an orca outright. In rosette formation, those tails all face outward in every direction at once. No matter which angle an orca approaches from, it faces a tail. The orca has to get past the tail to reach the softer belly, the head, or the calf in the center. And getting past the tail of an animal that weighs 60 tons is not a simple thing. The rosette also pulls the group's sonar into one location. When all the adults are clicking at the surface in close formation, they generate an enormous amount of sound. Any orca that approaches hears that wall of noise coming at it, and knows exactly how many whales are in the group. There's something else the rosette does that's less obvious. Injured or exhausted whales can hold formation. In a group of 8, even 3 healthy adults with functioning tails represent a serious threat. The weakest members of the group benefit from the strength of the others. The calves, which are the orca's real target, stay completely shielded in the center of the flower, protected on all sides by adult bodies. But the rosette has a weakness. It only works as long as every whale stays in position. The moment one animal gets separated, the circle breaks, and the orcas know this. Every orca attack on a sperm whale pod follows the same basic strategy. Find the weakest animal and pull it out. They don't try to break through the tails. They work the edges. They harass. They come in and back off, come in and back off, each time nudging the group slightly, looking for the whale that hesitates, the one that's already tired, the calf that drifts half a foot too far from the center. One gap. That's all they need. And when they find it, the entire dynamic of the encounter changes in a matter of seconds. The rosette is a remarkable invention. It emerged from millions of years of being hunted, and the fact that sperm whales still need it is a reminder that even the loudest animal on Earth, carrying the most powerful biological weapon ever discovered, is not untouchable. The attack that proved this happened in October 1997, 130 miles off the coast of California. October 1997. A research vessel 130 miles off the coast of Central California. Biologist Robert Pittman and his team are at sea, studying marine mammals when they spot something that has almost never been witnessed and never been studied at this scale. Approximately 35 killer whales are attacking a pod of 9 sperm whales. Pittman and his team watched for 4 hours. They took notes, they filmed what they could. What they wrote afterward became one of the most studied papers in marine biology. The orcas attacked in waves. Groups of 4 to 5 female orcas at a time, some with calves alongside them, came in and struck. They weren't trying to kill in a single rush. They bit, raked, and tore, then pulled back and let another wave come in. Scientists call this the wound and withdraw strategy. The idea is to weaken the target progressively. Each wave inflicts a little more damage. Each withdrawal gives the attackers time to recover while the sperm whales cannot. It's a strategy built for a long fight. The 9 sperm whales formed a rosette immediately. They pushed together, heads pointing in, tails pointing out, and held position. And they held it for a very long time. The orcas came in wave after wave, and the whales at the edges of the formation took the hits but didn't break. But the rosette has a cost. Holding formation at the surface for hours is exhausting. Sperm whales are deep-diving animals. They spend their lives in motion, surfacing briefly to breathe, sitting still at the surface, getting struck repeatedly, uses energy the whales can't replace during the fight. Pittman watched as the formation slowly degraded. Animals that had taken damage drifted slightly out of position. Others, trying to cover those gaps, exposed different angles. The orcas noticed every shift. Then the male orcas, who had been hanging back, barely visible at the edge of the fight, moved. Adult male orcas are significantly larger than the females. In this encounter, they had stayed completely inactive through 4 hours of sustained attack. One male finally charged in toward a single sperm whale that had been gradually separated from the group. The sperm whale was badly injured. The male orca covered the distance fast and killed it. Pittman's team described the scene as deeply unsettling. The sperm whales had tried everything. They held their formation, covered each other's gaps, and stayed in tight contact even as individuals were damaged. But under sustained attack from 35 coordinated animals, the math eventually stopped working in their favor. The remaining 8 sperm whales survived. The orcas, perhaps satisfied with one kill or perhaps exhausted themselves, broke off. Pittman wrote that the most striking feature of the attack was the apparent helplessness of the sperm whales during the worst moments, despite their size and their weapons. When the formation held, they were formidable. When it broke, they were vulnerable. The ocean keeps score, and this encounter suggested the score was closer than anyone had assumed. There's one detail from Pittman's account that stayed with other scientists for years. The male orcas waited. Most predators go for the kill as fast as possible. Speed is safety. The longer a hunt takes, the more chances something goes wrong. A prey animal fights back. An injury slows the predator. Another predator smells blood and shows up to take the meal. Fast kills are efficient kills. Orcas hunting sperm whales throw that rulebook away. The wound and withdraw strategy is patience weaponized. Female orcas, often with their own calves swimming alongside them, form small attack groups of 4 or 5. They come in from one direction at a time. They make contact, bite, rake, strike, and then immediately pull back before the sperm whale's tail can connect cleanly. The attack lasts seconds. The withdrawal lasts longer. Then another group comes in from a different angle. This rotation serves several purposes. First, it means no single orca takes too much risk. A sperm whale tail, even from an exhausted animal, can deliver a blow powerful enough to fracture ribs. By hitting and retreating, each wave of attackers avoids the worst of the counterattack. Second, the rotation is relentless. The sperm whales get no break. While one wave retreats, another is already moving in. The cumulative damage builds without pause. But the most important effect is on the rosette itself. Each attack nudges the formation slightly. A whale at the edge of the circle recoils from an impact and shifts half a body length. The next one covers for it but moves out of its own original position. The orcas study these micro-shifts. They probe the edges constantly, not to break through immediately, but to map which whales are weakest, which gaps are forming, which individual is drifting. This is where the intelligence of orca hunting becomes something genuinely hard to understand. They are running a tactical analysis in real time across a group of 35 individuals, while conducting a physical attack on animals much larger than themselves. Each wave of attackers needs to know what the previous wave found. They share this information, researchers believe, through short post-attack vocalizations while the next group is preparing to go in. Even in a hunt, they're talking, just not during the approach. The sperm whales fight this by doing the opposite. They tighten the circle. When an individual gets hit and flinches, the animals immediately adjacent to it push inward, closing the gap before the orcas can exploit it. In Pittman's 1997 observation, one sperm whale that was seriously damaged and had been partially pulled from the rosette was guided back by 2 others who left their own positions to flank it and steer it home. Those 2 whales exposed themselves to attack to recover the injured one. That detail has fascinated researchers ever since. It suggests the sperm whales aren't just following instinct and holding a shape. They're making decisions. They're choosing to accept risk individually to preserve the group's integrity. 2 kinds of intelligence. One rotating, patient, tactical, picking apart a defense. The other cooperative, self-sacrificing, holding together under pressure. The question is what happens when the defense finally gives. Watch the footage from any documented sperm whale attack. The female orcas are everywhere, coming in, pulling back, circling, probing, striking. The calves stay at the edge, watching. And the adult males are almost invisible. They're there, but they're barely moving. The largest orcas in any pod are the adult males, sometimes reaching 30 feet in length and weighing 12,000 pounds. By any measure, they're the most powerful animals in the group, and in a fight against a massive sperm whale, their size and strength would be enormous assets. Yet in documented attacks, the males hang back while the females do most of the work, sometimes for hours. This isn't weakness, it's strategy. Orca pods are built around family lines. The core of every pod is a group of females, mothers, daughters, sisters who stay together for life. The males within the pod are their sons and brothers. The females hunt cooperatively because they have hunted together since birth. They know each other's movements, tendencies, and strengths in the way that only a family that has worked together for decades can. The males are valuable in a different way. They're the finishing move. By holding the males back during the grinding wound and withdraw phase, the pod preserves its heaviest weapons for the moment when they're most needed. When the rosette finally begins to fragment, when one sperm whale is separated from the group and is already weakened and injured, the calculation changes. A damaged, isolated sperm whale is still dangerous. It can still turn, still thrash, still inflict serious harm, but it's no longer protected by its neighbors' tails, and it can't escape. That's the moment the male orcas move. In the 1997 California attack, Pittman watched one large male orca stay completely stationary at the edge of the encounter for nearly 4 hours while the females worked. Then a single sperm whale was separated and severely injured. The male charged in from a distance. It covered the gap in seconds. It struck once, precisely, and the fight was over. 4 hours of patience. 10 seconds of action. This timing isn't accidental. Males who charged in early with the females would have been exposed to the full defensive capability of an intact sperm whale group. The probability of a serious injury was much higher. By waiting until the defense had been degraded, the male essentially reduced his personal risk to near zero while contributing the killing blow. From the outside, it might look like the males are letting the females do all the work. What's actually happening is a division of labor so efficient that it's been refined over millions of years of selective pressure. The animals that got this wrong didn't leave descendants. The ones who mastered the timing did. What the males are watching while they wait is worth thinking about. They're reading the whole picture. They're monitoring the state of the rosette, the energy of each female wave, the condition of the targeted sperm whale, and somewhere in that calculation, they know exactly when the moment has arrived. There's one more weapon the sperm whales have that even the males didn't expect the first time they encountered it. The calf is the reason for everything. Orcas attacking a sperm whale pod aren't after the largest adult. Adult sperm whales are simply too dangerous and too tough. They've been hit before. They know how to fight back. And killing a healthy adult in full rosette formation might take more energy than the meal is worth. The calves are the target. They're smaller, softer, and nutritionally rich, and they can't defend themselves. The rosette is built entirely around this fact. Every element of the formation prioritizes the calf's survival. When the adults pull into a circle, the calves press inward to the very center. The orca's path to the calf runs through the adults' bodies first, then their tails, then a tight cluster of additional adults, and finally to the calf itself. The geometry of the formation makes the calf the most defended point in the entire structure, and the adults reinforce this with behavior. In documented attacks, adult sperm whales that have taken hits and are injured will still hold their position in the outer ring. They don't push their way to safety in the middle. They absorb the damage and stay between the orcas and the young. In some observations, adults have been struck multiple times in the same encounter and refused to break formation. The injuries were visible and serious. The behavior didn't change. This points to something in the sperm whale social structure that goes beyond instinct. Sperm whales live in matriarchal family groups. An older female leads the group, and the structure around her is built from daughters, granddaughters, and the calves of all these animals. Every calf in the center of that rosette is connected by blood to most of the adults on the outside. The adults aren't protecting a stranger. They're protecting their own genetic future. From a biological standpoint, an adult female sacrificing some of her own tissue to protect a calf that carries her genes is rational. But the degree of sacrifice observed in these encounters goes well beyond what simple self-interest models predict. Whales returning to position after serious injury suggests something more complex is happening. Some marine biologists use the word culture. Sperm whales learn from each other. Calves watch how adults respond to threats. Adults have seen previous attacks. The behavior in the rosette isn't purely genetic programming. It's partly learned, passed from one generation to the next through direct observation. The orcas know the calf is in the center. They always know this. Their entire wound and withdraw strategy exists to peel the formation apart until they can reach it. And the sperm whales know that the orcas know. The whole encounter is both animals doing exactly what the other predicts, simultaneously trying to find the edge case where the prediction fails. Sometimes the orcas find it, sometimes they don't. But in 2024, off the coast of Western Australia, a group of sperm whales introduced an element no orca had apparently prepared for. A whale-watching boat off Bremer Canyon, Western Australia, 30 miles offshore. Marine biologist Jenna Tucker is on deck, watching a group of orcas move through the water in what looks like a foraging pattern. Deep dives, long surfaces, standard behavior, then everything changes. 4 adult sperm whales and 1 juvenile appear at the surface nearby. The orcas immediately shift behavior. They stop foraging and begin circling the sperm whale group. The sperm whales pull into a tight cluster at the surface, their bodies pressing together. Tucker watches through binoculars. The guests on board watch with her. The encounter is tense, but, for now, still. Then, a large dark cloud rises from the water. Tucker described it as a reddish-brown bubble, expanding rapidly at the surface. The smell reached the boat before anyone fully processed what they were seeing. One of the sperm whales had released an enormous cloud of liquid waste into the water, and then, with deliberate sweeps of its tail, spread that cloud across the widest possible area. The water around the group turned dark brown. The cloud spread fast, covering a patch of ocean roughly the size of a basketball court. The orca nearest to the sperm whale group pulled back. Then they all pulled back. One orca, a female, the researchers called Wonks, had been positioned directly behind the sperm whale when it released the cloud. Wonks was hit with the full force of it. She veered away immediately. The orcas regrouped briefly, circled the outside of the cloud, and then left the area entirely. The encounter had lasted over an hour before the discharge. Within minutes of it, the attack was over. Tucker later said it looked like the orcas said, collectively, "Not worth it, let's go." The scientific community took this seriously. Defensive defecation, using waste release as an active defense, has been observed in other animals. Squid use ink, some insects spray chemicals. But for a sperm whale to deploy it in a directed, tactical way against a sustained predator attack was something no one had clearly documented before. The sperm whale did not simply empty its bowels out of fear, though fear may have contributed. It released the waste and then actively fanned it with its tail. That second step, the deliberate spreading of the cloud, suggests something more intentional. Passive release doesn't produce a basketball court-sized barrier. Tail movement does. Scientists are cautious about calling this fully conscious strategy. The jury is still out on exactly how deliberate the behavior was. But the physical sequence, release, and then tail spread, is hard to explain as accidental. What the cloud actually did to the orcas is still an open question. It may have been the smell. It may have been the visual confusion of the cloud obscuring the whales inside it. It may have been the texture of the water changing the acoustic environment, making the orcas' sonar harder to read in the contaminated zone. Possibly all three at once. Whatever the mechanism, the outcome was clear. The orcas left. The sperm whales survived. And somewhere in that reddish-brown cloud, an ancient and deeply unglamorous defense weapon had just worked against the ocean's most sophisticated predators. The orcas didn't leave because the smell surprised them. They live in an ocean full of biological material. They've swum through blood, through decomposing animals, through every kind of organic matter the sea produces. Smell alone doesn't move an orcapod that has spent an hour pursuing prey. Something about the cloud itself changed the encounter in a way that mattered. Scientists have 3 main theories, and the honest answer right now is that all 3 might be partially correct. The first involves vision and disorientation. Orcas rely heavily on both sight and sonar when attacking large prey at close range. The rosette formation works in part because the orcas can see the gaps in it and read the positions of individual whales. A dense, expanding cloud of material at the surface disrupted that visual map entirely. The orcas circling just outside the cloud suddenly lost their ability to see which whale was which direction the group was moving, and where the calf was positioned inside the formation. They were targeting specific gaps and specific animals, and the cloud wiped out that information in seconds. The second theory is acoustic. Sonar works by sending a signal and reading the echo. A dense mixture of particles suspended in water changes the way sound propagates through it. The sperm whale's fecal cloud, packed with organic material, may have created enough acoustic scatter to make the orca's own sonar difficult to interpret near the cloud's surface. Their signals were returning distorted. The image they were painting with sound became blurry. The third theory is the most straightforward and the most debated: chemical deterrence. Some researchers think the waste contained compounds unpleasant enough at high concentration to cause discomfort in the orca's mucous membranes, their eyes, or their breathing. Orcas breathe at the surface. If the cloud was concentrated enough at the waterline, surfacing to breathe inside, it would have been genuinely aversive. Jenna Tucker, who observed the encounter, leaned toward the visual and acoustic explanations. In her account, the orca called Wonks didn't flee in apparent pain. She veered away in apparent confusion, regrouped with the others, and then the whole pod reassessed. It was the reassessment that ended the attack. The orcas weren't driven off by force. They made a calculation. The cost of continuing had just increased significantly. The target was now invisible inside an unknown medium. The risk of injury had gone up. The payoff hadn't changed. In orca terms, the math stopped working. What Tucker's account also reveals is something about sperm whale intelligence that goes largely undiscussed. The fecal release alone is a passive event. Any frightened animal might lose bowel control under attack. But the tail fanning, the deliberate spreading of the cloud, is a separate, active behavior requiring physical effort during an ongoing predator attack. The whale chose to allocate energy to spreading the defense while simultaneously maintaining formation and signaling to the rest of the group. That's multitasking under extreme pressure. From an animal most people still imagine as a slow, passive giant of the deep, the sperm whale and the orca have been running this arms race for tens of millions of years. Every tool one side develops, the other eventually counters. The rosette, the wound and withdraw, the acoustic stealth, the fecal cloud. And yet neither side has found a permanent solution. What we haven't talked about is how the sperm whales know the orcas are coming in the first place. Because by the time an attack begins, the sperm whales have often been preparing for longer than you'd think. The orcas think they're approaching in silence, but they announced themselves an hour ago. Mammal-hunting orcas go quiet during the stalk. Their echolocation clicks drop. Their social calls stop. From above, from a boat, from any visual vantage point, they appear to be moving without a sound. Researchers watching them for the first time often assume the sperm whales have no warning until the orcas are close. The ocean tells a different story. Sound moves through water at almost 1 mile per second. A group of mammal-hunting orcas, even operating in near silence, produces noise. Their bodies create pressure waves as they swim. Their breathing breaks the surface. Any echolocation clicks they do use, even sparse ones, travel outward in every direction. And orca calls, when they make them, can travel through the ocean sound channel for miles before fading below the threshold of what a sperm whale's ear can register. Sperm whale hearing is tuned between 5 and 20 kHz. Orca calls cluster near the lower end of that range, around 1 to 2 kHz, which is slightly below peak sensitivity for the sperm whale. But it's detectable, like hearing a sound through a closed door. You can't make out every word, but you know something is out there. In practice, this means a sperm whale can detect the acoustic signature of an approaching orca pod well before the orca pod is close enough to see the whale or track it precisely. What happens next is where things get interesting. Scientists in the Norwegian Sea ran a careful experiment. They attached multi-sensor tags to 5 male sperm whales and monitored their behavior over extended periods. The whales were diving normally, clicking rapidly as they hunted squid in the deep. Then the scientists played underwater recordings of mammal-hunting orcas through a speaker near each whale, carefully monitoring what the animals did next. The whales stopped foraging. Every one of them interrupted their deep hunting dives and began moving toward the surface. Their click rates dropped sharply. And then, despite being solitary animals that normally spend hours alone, they began moving toward each other. The males clustered. Alone on the surface, they wouldn't be able to form a full rosette, but they pushed their bodies together into small groups, oriented themselves with tails outward, and held position. They assembled a partial defense entirely from a recording played by scientists. The implication is significant. In a real encounter, sperm whales pick up orca sounds from much farther away than the experiment simulated. They have more time to prepare, more time to call for other whales, more time to converge from different directions and form a stronger group before the orcas even arrive. The orca's silence during the final approach doesn't erase the acoustic trace it left behind for the previous hour, and the sperm whale has been listening to the whole thing. This raises a question that scientists find hard to answer cleanly. Are the sperm whales responding to a type of sound, the general category of orca call, or do they recognize something more specific? Do they know how many orcas are coming? Can they tell a fish-eating orca from a mammal-hunting one? The research suggests they can at least tell the difference in some cases. But exactly how much information they're extracting from those distant sounds is something researchers are still working to understand. What we do know is that by the time an attack begins, the sperm whales are rarely caught completely off guard. Male sperm whales are supposed to be loners. That's the received wisdom in marine biology. Adult females live in tight family units, always together, always communicating. Adult males leave the group when they mature and migrate to colder, deeper feeding grounds where they spend most of their time alone. In the Norwegian Sea, a researcher might tag a male sperm whale and watch it spend 6 or 8 hours without approaching another whale at all. Solitary, quiet, focused entirely on hunting. Then you play orca sounds nearby, and the entire picture falls apart. The 2013 study in the Norwegian Sea was built around this exact observation. A team led by researcher Charlotte Thuret and colleagues from multiple European institutions attached acoustic tags to 5 male sperm whales, each one foraging alone. The tags recorded every click the whale produced, tracked its depth and movement, and logged the angle and speed of each dive. Then the team lowered a speaker and played sounds of mammal-feeding killer whales. Every tagged whale responded. The first thing each whale did was cut the dive short. A normal foraging dive for a male sperm whale in Norwegian waters goes deep, sometimes over 3,000 feet, and lasts up to an hour. These whales were pulling out of their dives after just a few minutes. They came up fast, much faster than a normal ascent. They surfaced and stayed near the top. The second thing they did was produce coda clicks. That was the detail that stunned the researchers. These were solitary males in a high-latitude feeding ground. The scientific literature on this population consistently noted that these animals almost never produce social codas. Codas are for family communication. They're the click patterns females and calves use to maintain the bonds of their group. Males in Norway weren't using them until orca sounds played nearby. Then they produced codas immediately. And the third thing they did was move toward each other. 2 whales that had been separated by a significant distance, each hunting alone, began slowly converging. They surfaced close together. They stayed near each other at the surface, in a way that looked, unmistakably, like the beginning of a defensive formation. Something about the sound of a predator activated a social instinct that the animals essentially hadn't used in months. They remembered how to be part of a group. They called for neighbors. They assembled. The researchers noted this was a surprise in every sense. Solitary male sperm whales were not expected to have strong enough social instincts to respond this way. The assumption had been that males, having left their natal groups, had moved beyond the cohesive defensive behavior of the matriarchal units. The experiment suggested the instinct never disappeared. It was dormant, waiting for the specific trigger. There's something worth pausing on here. An animal that has been alone for weeks, hunting in silence miles from its nearest neighbor, hears the sound of danger and immediately tries to form a family group. The ocean around it goes quiet in a new way. It's listening for a response. And sometimes, the response comes. The 5 whales weren't cooperating. Nobody told them what to do. Nobody rewarded them for the right behavior. The researchers just played a sound and then watched what happened on the data feed coming back from the tags. Here's what the data showed, second by second. Whale number 1 was at depth, several hundred feet down, clicking rapidly during what the tag data identified as a prey capture sequence. Its click rate had accelerated into the short, rapid bursts called creaks, which happen in the seconds before and during a squid catch. Then the orca playback began above it. Within minutes, the click rate dropped, then stopped. The whale turned from its horizontal hunting position and began moving vertically toward the surface. It ascended faster than normal. It broke the surface and stayed there. Whale number 2 was resting, hovering near the surface in a behavior the researchers called logging. Motionless, quiet, recovering energy between dives. When the orca sounds started, it began producing clicks within seconds. It moved away from the speaker's direction. It surfaced within a short distance of the first whale. The others followed similar patterns, each from a different behavioral state. One was mid-dive. One had just surfaced from a long dive. One appeared to be traveling. All 5, regardless of what they were doing, changed direction toward the surface and toward each other. This matters for a reason beyond just the predator response. These whales were not in danger. The speaker was not an orca. No attack followed, but their bodies responded as if it were real, as if the threat were genuine and close. And importantly, their response was not to flee. It was not to dive deeper, which would have been the obvious escape strategy for an animal that can reach depths no orca can follow. A sperm whale can dive to over 6,000 feet. Orcas struggle below 2,000. The escape hatch of the deep ocean was available to every one of these animals. None of them used it. They all came up. They clustered. They prepared to stand their ground. Researchers found this puzzling and significant. The study paper specifically noted that the sperm whale's response defied simple predator avoidance logic. Going up toward an orca is not the obvious survival move, but the defensive rosette is a surface behavior. It only works when the whales are together at the top, and a calf, which the males in this study didn't have, can't dive deep to escape. The behavior seems to be a fixed response, older and deeper than individual calculation. When the sound arrives, the body does what generations of survival shaped it to do: surface, cluster, hold. It's a strategy written into the animal at a level below conscious thought, and it makes the silence of the approaching orcas, the strategy they've refined over millions of years, feel almost poetic in its opposition. One species trying to be invisible with sound, the other surfacing to face whatever comes. The next part of this story is the detail no one expected. Every biologist who has watched a sperm whale under orca attack has asked the same question. The whale can dive to 6,000 feet. Orcas stop being effective below 2,000, maybe 3,000 at a stretch. The gap is enormous. The escape route exists. Why don't the whales use it? Robert Pittman asked this directly in his paper about the 1997 California attack. Over 4 hours, while 35 orcas struck again and again, the 9 sperm whales never attempted to dive. Even during the brief windows when the orcas pulled back, when the water around the rosette was temporarily clear, the sperm whales stayed at the surface. Not one of them went down. The experiment in Norway showed the same thing. Solitary males who could have easily dived below orca range chose instead to surface and stay. There are several possible explanations, and none of them are fully satisfying on their own. The first is the calf. Sperm whale calves cannot dive as deep or as long as adults. They need to breathe frequently. A family group that dives in response to an orca attack leaves its youngest members behind, floating alone at the surface with no protection. The orcas, who are targeting the calf, would simply wait at the surface and take it. Diving to escape is only viable if you're willing to sacrifice what the orcas came for in the first place. The second explanation is about the orcas' own capabilities. Orcas can dive. They're not restricted to the surface. Researchers have documented orca dives beyond 1,000 feet. A sperm whale descending to escape might find that the orcas simply follow it to a depth where the whale's sonar gives the orcas more information, not less. In the dark, the sperm whale's clicks illuminate the space around it. The orca listens. The whale becomes the one broadcasting its own location. The third explanation is stranger, and perhaps the most honest. The behavior may be older than the tactical problem it now faces. The rosette is an ancient response, shaped over millions of years when the specific threat profile was different. The animals surface and cluster because that's what worked, and what their genes remember working, across enormous stretches of time. Evolution doesn't optimize in real time. It optimizes across generations. The instinct persists, even when the math of a specific encounter might favor a different choice. Scientists mark this openly as an unresolved question. They don't fully know why the whales stay up. What they do know is that the whales who stayed up and held the rosette survived at a higher rate than those who drifted away from it. The formation works, even imperfectly. The ones who held it lived to teach it to their offspring. And somehow, out of all the strategies these animals could have chosen, this is the one that persisted. No moon, no stars visible below the surface. At 200 feet down in the Norwegian Sea in summer, there is barely any light at all. The orca is moving, but not clicking. It has been silent for minutes. There's nothing in the water that could tell a seal the predator is close, and yet the orca is tracking the seal precisely. Researcher Volker Dieck discovered this while studying mammal-hunting orcas in southeastern Alaska. The orcas he followed were almost completely silent during hunts. No echolocation, no social calls. But they were finding prey in the dark. Something was guiding them. The team spent months trying to understand what it was. The answer was passive listening. Every animal that breathes at the ocean surface makes noise when it does so. A seal coming up to breathe produces a small splash, a burst of sound as air moves through its respiratory system, the brief acoustic signature of a living body at the interface between water and air. A porpoise produces its own faint clicks as it hunts fish nearby. A whale surfaces with a blow. All of these sounds propagate downward through the water column and outward in every direction. The mammal-hunting orca learned to receive all of it. It stopped broadcasting and started receiving. It moved silently through the dark and listened for the sounds of whatever it was hunting. When the sounds got louder, it turned toward them. When they stopped, it adjusted its heading and waited. It hunted entirely by the noise its prey couldn't avoid making. In one of Dieck's recordings from a juvenile orca, the team captured something extraordinary. They heard, very faint and distant, the calls of harbor seals. Over the next several minutes, those calls grew steadily louder, coming closer, though nothing on the surface indicated the orca's direction. Then 3 sharp roars from the seals. A brief, violent burst of sound, then silence. The orca had tracked those seals across open water entirely by ear and had reached them without giving any acoustic signal of its own approach. After the kill, the orcas became loud again, vocalizing, coordinating, communicating over how to share the prey. The silence had served its purpose. Communication resumed the instant the hunt was over. This behavior is not instinct in the simple sense. It requires inhibiting vocalization while simultaneously processing incoming acoustic information. It requires patience across a sustained stalk, and it requires coordinating multiple individuals in silence, all converging on the same target without the usual calls that orcapods use to stay organized. The ocean is not empty in the dark. It's full of quiet signals. The orca learned to read them all while saying nothing itself. The next question is, what happens when the prey is making sounds loud enough to rattle bones from 100 feet away? Two groups of orcas live off the coast of the Pacific Northwest. They share the same water. They sometimes swim within sight of each other. They are so closely related that to a casual observer they look identical. Their DNA overlaps significantly. And yet they are, in almost every measurable behavioral way, completely different animals. The first group eats salmon. They are among the noisiest creatures in the ocean. They call constantly, whistle to each other, use a library of group-specific calls that researchers have mapped and catalogued for decades. They click rapidly when they hunt, sometimes firing echolocation bursts at rates that fill the water with sound. A hydrophone dropped anywhere near a pod of fish-eating orcas will register continuous acoustic activity for hours. The second group eats marine mammals, seals, porpoises, dolphins, occasionally larger whales. During the stalk phase of a hunt, they go almost completely silent. This difference isn't cultural in the narrow sense, it's functional. Salmon don't hear well in the frequency range orcas use. An orca can shout its location to its entire family, click at maximum power to find fish, and coordinate loudly at the surface. And the salmon has no idea. The noise costs nothing. A harbor seal hears exactly as well as an orca. A porpoise hears better. Beaked whales have some of the most sensitive ears of any mammal, tuned precisely to the range that orcas use to echolocate. If the mammal-hunting orca clicks normally during a hunt, the prey hears it coming, adjusts, and the orca misses. The noise costs everything. So the two populations evolved in opposite acoustic directions. One grew louder because loudness was free. One grew quieter because noise was fatal. And after enough generations, the difference became so ingrained that the two groups don't just hunt differently, they live differently. Their social calls diverged. Their group sizes changed. Their ranges shifted. The acoustic constraint on one group reshaped its entire way of existing in the world. Researchers call this process character displacement. When two similar species or populations share territory and compete for resources, the ones that develop the strongest differences survive best. The fish-eating orcas and the mammal-hunting orcas diverged in the most fundamental possible way: what they're willing to say and when. Scientists who have studied them together for decades describe encountering both types in the same area as one of the strangest experiences in marine fieldwork. One group fills the water with noise, the other glides past in near silence. They can see each other but don't interact. They seem to inhabit different acoustic worlds despite sharing the same physical one. The prey that shaped this divergence had no idea it was happening. It was just trying to survive, one breath at a time. Picture this: an orca pod is hunting. The orcas are some of the most effective predators on Earth. They've brought down blue whales. They've outmaneuvered great white sharks. They coordinate with a sophistication that marine biologists have compared to wolf packs. Then the pilot whales show up, and the orcas leave. This is one of the most baffling dynamics in the ocean, and researchers published fresh evidence about it in early 2026. A team studying orca responses to different acoustic stimuli played recordings of long-finned pilot whale calls to free-ranging orca pods. The orcas responded exactly as they respond to naval sonar. They tightened their formation, reduced their wandering, went quiet, and left the area. All of this happened just from hearing a recording. The pilot whales weren't even there. Long-finned pilot whales are much smaller than orcas. They eat squid primarily. There's no documented case of a pilot whale killing an orca. They don't compete for the same prey in a direct way. By any simple analysis of the food chain, they have no business making orcas nervous. But in the ocean off Iceland, pilot whales have been observed approaching orca pods at high speed and chasing them away. Not fleeing, chasing, and not in response to an attack. The pilot whales initiate it. They converge on the orcas in a coordinated surge, surrounding them with noise and physical presence, and don't stop until the orcas move off. The orcas move off. Scientists have several theories for why. The first is scale. Pilot whales travel in large groups, sometimes hundreds of individuals. Even if a single pilot whale is not a match for a healthy orca, A coordinated charge from 50 or 100 of them represents a different kind of threat. The sheer weight of their combined acoustic output, dozens of large animals calling simultaneously, creates a wall of noise that may be genuinely aversive to the orca's sensitive ears. The second theory is that the orcas have learned, across generations, that engaging with pilot whales carries risk with almost no reward. Pilot whales are aggressive, fast, and willing to make physical contact. For an orca, any injury is costly. An injured orca hunts less effectively. Even a small risk of injury from a species you have no particular need to eat makes avoidance the logical choice. The ocean's apex predator has effective enemies. They just don't look like what you'd expect. And the sperm whale is watching all of this from the deep, still clicking. There's a pattern in every recorded mammal hunting orca attack. It shows up in the Alaskan data. It showed up in Pittman's California observations. It shows up in recordings from Norway and from Australia. The pattern is this: before and during the hunt, near silence. After the kill, noise. Scientists initially noted this as a hunting strategy. Go quiet to avoid alerting prey. Get loud when the prey is already caught because noise no longer matters. That explanation is accurate as far as it goes. But there's a second layer that researchers have been studying more carefully. The post-kill vocalizations are specific. They're not random celebration or general excitement. They appear to contain coordinated information about what happens next, how to position bodies around the prey, which whale takes which section, how the food gets shared between individuals of different ages and ranks within the pod. Killing large prey requires careful dismemberment. The orca's mouth isn't built to swallow a whale calf whole. Someone holds it, someone else strips it. The communication that resumes after a kill is functional, detailed, and organized. Researchers studying orca pods in Alaska recorded a juvenile orca during a seal hunt. After the seal was killed, they heard tearing sounds, bone sounds, and a rapid exchange of calls between the juvenile and adults nearby. The calls weren't random. They seemed to coordinate movement around the carcass. The specific calls used during this sharing phase differed from the general social calls the pod used while traveling or resting. This creates a picture of two very different acoustic modes, operating in the same animals, switched on and off based on circumstance. Travel mode is social and vocal. Approach mode is near silent. Kill mode is tactical and specific. Post-kill mode returns to social. The pod cycles through these states with apparent ease, and each member seems to know which mode is active without being explicitly told. For orcas hunting sperm whales, the silence phase lasts longer and the stakes are higher. The approach can take an hour. The wound and withdraw attack can stretch across 4 hours, as in the California case. Through all of that, the communication has to happen in near silence or not at all. Yet the coordination remains intact. How? Nobody knows completely. The leading theory is that body positioning substitutes for some of the vocal coordination. Orcas can see each other underwater. Swimming side by side at a specific angle may communicate something that a call would otherwise convey. Subtle changes in speed, in fin angle, in proximity to specific individuals in the group could carry information that the acoustic record doesn't capture. The silence isn't absence of communication. It's communication in a different channel, and somewhere in the ocean, the sperm whale is trying to decode every part of it. The Atlantic and Pacific Oceans have different accents. This is the cleanest way to describe what scientists have found when they compare sperm whale coders across different ocean basins and different regions within those basins. The click patterns that sperm whale groups use to communicate aren't random. They're structured, they're consistent within groups, and different between groups. And they're learned, passed from mother to calf over years of close contact at sea. Researchers studying sperm whales off the Caribbean island of Dominica identified a pattern in the eastern Atlantic that uses codas with 5 regular, evenly spaced clicks, followed by a pause. Scientists call this type the 5R pattern, where R stands for regular, A group that shares this coda will only socialize closely with other groups that share it. Units from different coda types live in the same water, sometimes swim in visible proximity, and largely ignore each other socially. The acoustic identity is real enough to act as a social barrier. In the Pacific Ocean, researchers identified at least 7 distinct vocal clans across different regions. As the spatial overlap between any two clans increased, their identity codas became more distinct from each other, following the same pattern found in human language communities. When groups share territory, their markers diverge as a way of maintaining clear identification. When groups are geographically separated, they can drift towards similarity because the need to distinguish is lower. This parallel to human dialect formation was not expected. Most researchers assumed whale communication would be too simple and too genetically fixed to show this kind of cultural nuance. The data showed something closer to the opposite. Calves learn codas from their mothers and from other members of their social unit. The learning takes time. Young calves produce imprecise click patterns that gradually sharpen over months or years toward the specific timing of their clan's identity coda. This is cultural transmission in the clearest biological sense. A behavior that is not genetically programmed, that varies between groups sharing the same genes, and that is passed through direct social contact from one generation to the next. 7 clans, 7 distinct dialects, occupying overlapping ranges across the world's largest ocean, recognizing each other by sound alone. The orca, moving through these waters in near silence, is entering a world that is more organized and more ancient than it could possibly know, and the organization runs deeper than anyone imagined until very recently. For decades, scientists described sperm whale codas as a kind of biological Morse code. Click patterns, gaps between clicks, rhythm, and tempo. The whale taps out a sequence. The sequence carries identity or possibly meaning, and another whale receives it. The analogy was useful. It was also incomplete. In November 2025, a team of researchers from Project CETI and the University of California, Berkeley, published a study that changed the picture. They were analyzing sperm whale codas through a linguistic framework rather than a purely acoustic one, and they found something inside the clicks that no one had been looking for: vowels. Human vowels are shaped by the position of the tongue and the shape of the vocal tract. They're defined by the spectrum of frequencies they contain, by which frequency bands are emphasized over others. The vowel sound in R has a different spectral shape than the vowel sound in E. These spectral shapes carry meaning independently of the rhythm or timing of the speech. When the Berkeley researchers analyzed sperm whale codas without the usual focus on click timing, they found 2 distinct spectral patterns appearing consistently across different whales: an alpha vowel pattern and an I vowel pattern. Whales could produce both in different combinations, in ways that added a second layer of variation to their codas entirely separate from the click rhythm. The lead linguist, Gaspar Begusch, described it this way: previous researchers had been reading the rhythm of whale clicks, the way you'd read the dots and dashes of Morse code. What he found was more like finding that each dot and dash also had a different color, and the color was carrying additional information. 156 distinct coda patterns had already been catalogued by Project CET. The vowel layer multiplied the potential combinations. The system was not Morse code at all. It was something substantially more complex, with structural features that matched predictions from linguistic theory about how complex communication systems are built. Begusch said the discovery made him reconsider his own field. Linguistics existed to study human language, and here was an animal, 60 tons, 400 feet down in the Caribbean Sea, organizing its voice in ways that linguistics had the tools to describe. What the clicks mean, what the vowels encode, whether this constitutes language in any sense a human would recognize, all of that remains unknown. The structure is there. The content is still out of reach. The animal with the loudest voice on Earth may also have one of the most complex ones. In 1950, a ship crossing the Atlantic produced a certain amount of low-frequency underwater noise. That amount was already more than whales had evolved to deal with. Since then, global shipping has increased low-frequency ocean noise by an estimated 32 times on major shipping routes. The ocean is no longer the acoustic environment that sperm whales spent millions of years adapting to. In July 2026, Project CETI published findings from 4 years of monitoring sperm whales off Dominica. The researchers analyzed nearly 1,400 coda recordings from 15 whales and compared the click patterns produced when ships were nearby versus when the water was quiet. The whales changed their communication. When ships were present, the whales shifted which coda features they emphasized. The aspects of their clicks most related to rhythm and timing changed most strongly. The researchers found that rhythmic features were actually the best predictors of whether a ship was nearby. Essentially, the whales were adapting their click structure in real time to the acoustic environment they found themselves in, the way a person raises their voice or changes the rhythm of their speech when trying to be heard over loud music. This is where the finding becomes worrying. The vowel structures discovered in 2025 are embedded in the spectral content of the codas. Shipping noise primarily affects low frequencies, the same range where many of the sperm whales' communication features sit. If the whales are already shifting their click patterns in response to ship noise, and if those shifts displace some of the subtle features that carry the most information, then the noise is potentially degrading the complexity of sperm whale communication, not just making it louder or harder to hear. What's being lost, exactly, is unknown. Scientists are careful about this. The whales may be adapting successfully. They may be finding alternative ways to convey the same information. But the evidence that the noise is changing something real, something measurable, in their communication is solid. The sperm whale spent millions of years developing the most sophisticated natural sound system on Earth. It built a language complex enough to contain something like vowels. It maintains cultural dialects that span entire ocean basins. And the primary threat to all of that, right now, is engine noise from cargo ships that most people will never see and never think about. Evolution doesn't happen in a moment. It happens across millions of generations of small, invisible advantages. An animal that avoids predation slightly better has slightly more offspring. Those offspring carry the slight advantage forward. Over enough time, what began as a small difference becomes a fixed feature. Here is one of the clearest examples of that process in the ocean. More than a dozen species of small dolphins and porpoises, spread across different oceans and unrelated to each other, share a striking similarity. They produce echolocation clicks at frequencies far above what orcas can hear. Regular dolphins click in the range that orcas hear well. These species click above that range, so high that orca ears can't fully register them. They gave themselves a biological cloaking device. Scientists call this acoustic crypsis. Crypsis means hiding. Acoustic crypsis means hiding through sound, or more precisely, through the deliberate placement of your sounds into frequencies your predator can't easily detect. These animals didn't make a decision to do this. Individual porpoises that happened by random variation to produce slightly higher frequency clicks were slightly harder for hunting orcas to detect acoustically. They were hunted slightly less often. They survived slightly more often. They produced offspring that carried the same tendency. Over millions of years, the click frequency drifted upward, generation by generation, until it crossed the orca's upper hearing limit. At that point, the echolocation clicks became essentially inaudible to the predator. What makes this more remarkable is that convergent evolution pushed multiple completely different lineages toward the same solution independently. Porpoises evolved it. Certain dolphins evolved it. A type of smaller whale evolved it. None of these groups are closely related. Each arrived at the same acoustic camouflage through completely separate evolutionary paths. The selective pressure from orca predation was strong enough to produce the same result in wildly different animals. The orca, sensing this pressure across millions of years, responded by going silent during hunts. If it wasn't broadcasting clicks, the prey's acoustic camouflage mattered less. The orca could switch to passive listening and find the prey through the sounds the prey couldn't avoid making. Back and forth. Click evolution. Silence evolution. The ocean writing its own slow negotiation between hunter and hunted in the structure of living animals. The sperm whale is the only prey animal in this arms race that chose the opposite strategy. Instead of going quieter, it went louder, so loud that the whole ocean had to reorganize around it. Remove the sperm whale from a stretch of ocean, and the change isn't just one animal missing. It's an entire acoustic and ecological anchor pulling loose. Sperm whales dive to depths of 3,000 feet or more, eat enormous quantities of squid and deep-sea fish, and then bring the waste products of those meals back to the surface when they breathe and defecate. The fecal matter they release near the surface is rich in iron and nitrogen, nutrients that fuel the growth of phytoplankton. Phytoplankton fuels everything above it in the food chain. The whale is physically moving nutrients from the deep ocean to the surface layer, like a pump, every time it completes a dive. When sperm whale populations in the Southern Ocean were reduced by commercial whaling over 2 centuries, that pump slowed. Researchers estimate that the sperm whales still absent from pre-whaling levels in the Southern Ocean represent a deficit of roughly 2 million tons of carbon per year that could have been drawn from the atmosphere by the phytoplankton their waste would have fertilized. 2 million tons of carbon every year that now stays in the atmosphere because the whales aren't there to move nutrients to the surface. But the disappearance of the sperm whale has a second effect that's harder to quantify and less often discussed. When sperm whales leave an area, the acoustic suppression they provide leaves with them. The clicking, the 230 decibel presence that makes orcas think twice about the entire patch of water. The orca now enters unchallenged. The animals that were getting an indirect buffer from the sperm whale's presence, the seals, dolphins, porpoises, and smaller whales that benefited from orca avoidance of sperm whale territory, suddenly face higher predation pressure. This isn't speculation. Researchers studying the relationship between whale populations and orca behavior have found that orca hunting pressure redistributes when large whale populations shift. When the big ones leave, the orcas adjust. The oceans that industrial whaling emptied of sperm whales didn't just lose a species. They lost a sound, and everything downstream of that sound changed. Recovery is slow. Sperm whale populations have grown roughly 4% per year since whaling protections began in the 1980s. They're rebuilding, but they haven't returned to pre-whaling numbers in most areas. The acoustic ecology they maintained for millions of years is still reduced. The silence where sperm whale clicks used to be is itself a form of damage. Researchers studying predator recognition in marine mammals have documented something remarkable in harbor seals. Seals can distinguish between the calls of killer whales that hunt them and killer whales that only eat fish. They respond with alarm to mammal-hunting orca calls and largely ignore fish-eating orca calls, even though both types produce sounds in similar frequency ranges. The discrimination is based on subtle acoustic differences in the call structure. The seals learned, over generations, to tell the relevant predator from the irrelevant one. Sperm whales do something similar at the broadest level. The Norwegian experiment showed they respond strongly to recordings of mammal-hunting orcas and respond less intensely to other sounds in the same frequency range. They have learned, somehow, to recognize the category of threat. But the deeper question is unresolved. Can they go further than category recognition? Can they recognize a specific pod, a specific individual, their own local predators versus strangers from a different ocean? Sperm whales live for 60 or 70 years. They have the largest brains of any animal on Earth, weighing up to 20 pounds, roughly 5 times heavier than a human brain. They maintain complex social relationships within their units and cultural knowledge across generations. The cognitive capacity to store individual acoustic signatures and recall them years later seems, in principle, available to them. And they have the data. An orca pod has a consistent set of calls that identify it. Researchers studying orca pods have mapped individual pod repertoires in detail. Each pod uses a specific set of discrete calls that other pods don't use. If a sperm whale has been attacked by a specific pod, it has been exposed to that pod's specific acoustic signature during an extremely high-stakes event, the kind of event that tends to produce lasting memory in intelligent animals. Whether a sperm whale that survived an attack from a specific pod then responds differently when that pod's calls appear in the water compared to a stranger pod's calls has not been formally tested. The data required to answer this would take years to collect. You would need to follow specific sperm whales, document which orca pods they've encountered, and then measure their behavioral responses to recordings of those specific pods versus other pods. The technology exists now that didn't exist 10 years ago. The answer may be coming, but right now, whether the sperm whale recognizes an old enemy by name is one of the ocean's open questions. Adult male sperm whales are the largest toothed predators on Earth. A fully grown male can reach 60 feet and weigh 60 tons. He has a head the size of a small truck and can produce a sound that rattles the ribcage of anyone within 100 feet. There is almost nothing in the ocean that should make this animal nervous. And yet, researchers who have followed individual males over multiple years in high-latitude feeding grounds consistently describe them as, in the words of one 2025 study, skittish. The study, titled directly for that observation, documented the behavior of adult male sperm whales in the Norwegian Sea across multiple orca encounter events spanning several years. What the data showed was a progressive change. After a harassment event, after orcas came in and circled and probed without completing a full attack, the male whales didn't simply return to normal behavior the next day. Their foraging dives got shorter, their surface time increased, their click rates during dives, the rapid firing that indicates active squid hunting, decreased. For days after a harassment event, the males operated in a state of elevated caution that measurably reduced their feeding efficiency. These are 60-ton animals with the loudest voice on Earth, and they were spending days eating less than normal because a group of smaller animals had circled them. The long-term cost of this is significant. Sperm whales need enormous amounts of food. A full-grown male burns through calories at a rate that requires sustained, efficient, deep hunting. Days of reduced feeding efficiency compound over a season. Repeated harassment events compound over years. The orcas, even when they don't manage to kill a whale, are reducing the prey's fitness through the cost of the fear itself. This is what biologists call the landscape of fear. Predators don't just kill prey, they shape the behavior of prey across time and space, even when no attack occurs. The places prey avoids. The behavior's prey changes. The energy prey spends watching instead of eating. All of it is a cost imposed by the existence of the predator, and it accumulates whether or not a hunt succeeds. The solitary male sperm whale, somewhere in the cold Norwegian Sea, cuts his dive short and surfaces early. No orcas are visible. The water seems clear. But 3 weeks ago there were orcas here. His body hasn't forgotten. 2 apex predators. 2 completely different strategies for using sound. One that went louder than anything else alive. One that learned to go quieter than almost anything else alive. They've been shaping each other for longer than our species has existed, and the negotiation between them still isn't settled. Here is what this standoff between sperm whales and orcas actually reveals beneath the biology. Intelligence in the ocean doesn't look the way we expected it to look. We spent centuries watching whales from the surface and assuming simple animals. Then we dropped hydrophones into the water and found something that organized itself into cultural clans, developed click dialects that spanned entire oceans, evolved vowel-like structures inside its communication system, and responded to acoustic threats with a social precision that most species don't approach. None of that was visible from above. All of it was in the sound. The orca's intelligence is just as hidden and just as extreme. The wolf of the sea isn't defined by its kills. It's defined by what it chooses not to do. Not clicking when clicking would betray you. Not rushing when patience outperforms speed. Letting the females do the grinding work for 4 hours, while the males hold position at the edge of a battle and wait for the precise second to move. That kind of restraint across an entire pod in a high-stakes encounter is not instinct, it's strategy. It's something that looks uncomfortable, like planning. Fear runs through all of this in both directions. The sperm whale's skittishness after a harassment event. The orca's caution around a full-sized sperm whale head. The fact that the ocean's loudest animal still forms a defensive circle when the right sounds arrive. The fact that the ocean's most sophisticated pack predator still turns away from a charging group of pilot whales rather than risk injury fighting something it doesn't need to eat. Fear is often described as a simple thing, an alarm response, a body preparing to flee. But what we see in the ocean between these two animals is something more specific. It's calibrated. It's learned across generations. It responds to information from miles away and adjusts before anything visible has happened. It's not separate from intelligence. It's one of the things intelligence is for, and underneath all of it, the ocean is still full of sound. The sperm whale's clicks travel 60 miles through the deep sound channel, carrying identity, location, and a language that took researchers 40 years just to start decoding. The orcas move through that sound in silence, listening to everything, saying nothing until the moment comes. What we heard in that data, when we finally started listening carefully, was not just two animals competing for food. It was two minds, shaped by the same ocean, running the same calculation in opposite directions, both of them still doing it. Right now, somewhere below us. That's where we end.